Hello and welcome to Physics Teacher. In this grade 12 chemistry tutorial, I'm going to go over about 5 questions from the acid-base equilibrium unit that we have. Now these 5 questions are from a review worksheet. If you want to follow along, you can get a copy of that review worksheet for free in the description along with all the answers. Let's start with question 6. This one says determine the pH of, so we have 2 options. Not 2 options, but 2 that we have to complete. So part A is for hydrochloric acid, and for part B is sodium hydroxide. So these are both strong acids and strong bases. So let's do part A. We have 1.2 liter aqueous solution containing 5 grams of hydrochloric acid. So let's first figure out the number of moles of hydrochloric acid. So the number of moles of hydrochloric acid is going to be mass over molar mass. So we've got 5.0 grams over molar mass, and you can check your periodic table for that. It's about 36.5 grams per mole. So that gives us 0.137 moles. Okay, once we have that, we can next look for the concentration of hydrochloric acid. Now concentration is moles divided by volume. So we just figured out moles. It's 0.137 moles divided by the volume, which they give us as 1.2 liters. And that gives us our concentration of 0.114 moles per liter. Now, since hydrochloric acid is a strong acid, we're going to get 100% ionization. So we can write the chemical equation like so. So we have hydrochloric acid colliding with water molecules, and it's going to go to completion. So this is not going to be an equilibrium. It's 100% ionization. We're going to get our hydronium ions, and we are left with our chlorine ions. So this is balanced. So we've got this 1-to-1 ratio here, and since we know the concentration of hydrochloric acid, we therefore know our concentration of our hydronium ions. It's going to be the same, 0.114 moles per liter. So now we can use our formula for pH, which is negative log of the concentration of hydronium. Since we know that now, we can plug this into our calculators, and we get the pH to be 0.94, so very acidic. We're going to do something similar for B. So for B, again, they give us mass and volume. So let's first start by figuring out the number of moles of sodium hydroxide. So that's just mass over molar mass. So you can check your periodic tables, just add sodium, oxygen, and hydrogen, and we get about 40 grams per mole. So that gives us about 0.045 moles. Okay, now this is a strong base. So NaOH is going to completely dissociate in water into its ions. So we got our sodium ions and our hydroxide ions. Now, since we know, I forgot to find the concentration. I was going to say, since we know the concentration of hydroxide, we know the number of moles of hydroxide. But let's just figure out the number of, the concentration of sodium hydroxide there. Okay, it's just going to be moles over volume, so 0.045 moles over, they give us the volume. We're going to change this into liters, so 0.75 liters. And we get a concentration of 0.06 moles per liter. Okay, now, since we know the concentration of sodium hydroxide and we have a 1-to-1 molar ratio, that means we also know the concentration of hydroxide ions, 0.06 moles per liter. So now we can go ahead. We can't find pH because we don't know how many hydronium we have, but we can find pOH, which is just minus the log of our hydroxide ions. And when we do that, we get a pOH of 1.22. Now, something else we know is that the pH plus the pOH is going to be a value of 14. So now we can indirectly figure out what that pH is by taking 14 and essentially we're bringing this over to the other side of the equation and subtracting 1.22. So we end up with a pH of 12.78. So there's our first problem. For our second problem, we're going to look at question number 11. This says determine the concentration of hydronium and hydroxide, then find the pH and the pOH of a solution prepared by adding 2.5 grams of benzoic acid to 750 milliliters of water. Okay, so benzoic acid, the equation is C6H5COOH, and this is going to combine with water. And this will not completely ionize, so we're going to have an equilibrium where one of these H's is going to donate to water to become hydronium. And then we're left with C6H5COO negative ion. All right, so just as before, we're given mass. So let's figure out how many moles that is. Let's just go to the side here. So the number of moles of benzoic acid is going to be equal to mass, 2.5 grams, over the molar mass of benzoic acid. So we add up all those on our periodic table. We get about 122 grams per mole. So this gives us 0.02 moles. And next, concentration. So what's the concentration of benzoic acid? Well, we know the number of moles now, and in the question, they give us volume. We're just going to convert that to liters, so 0.75 liters, and concentration is moles divided by volume. And that gives us a concentration of 0.027 moles per liter. Okay, now in this case, we can't just do our regular stoichiometry and mole ratio because this is an equilibrium equation. So we're going to need to use our equilibrium law. So let's start with our acid constant. And that's going to equal the concentration of our products. So we've got hydronium here. Okay, and then we have our benzoate ion. All divided by benzoic acid. Now, water is a liquid that gets included into our equilibrium constant, so we don't include it with our reactants. Okay, let's do a little ice table. So, ice table is good to help you. Right? We did this in our previous equilibrium unit, and we're not away from that because we have an equilibrium equation here. So for the ice table, I'm just going to label this as 1, 2, 3. So we're going to look at those concentrations of 1, 2, and 3. So initially, we have 0.027 moles per liter of benzoic acid. Okay. and nothing else. Then what happens is now we can look at our molar ratios. Now it is all 1 to 1 to 1 to 1 to 1, which is good. So we just have plus X and plus X. Okay, so hydronium and benzoate, we get plus X and plus X. And similarly, with this 1 to 1 ratio, this one's going to lose a certain amount of X. And they're going to end up with an equilibrium concentrations of XX and 0.027 minus X. So we can throw those into our equation here. Okay, so we've got Ka. It's going to equal, so X times X. So we're going to have X squared on the numerator. And in the denominator, we're going to have 0.027 minus X. Now, the Ka value, we can look up on a table. You can Google it. If you have a table from your chemistry class, you can look it up. Okay, it is 6 for benzoic acid. It's 6.5 times 10 to the minus 5. And that equals, once again, X squared over 0.027 minus X. Now that's a bit of a tricky equation to solve. It's not too bad, but we can simplify it a bit. How are we going to simplify it? Well, I'm going to eliminate this X. And I can do it because if we look at this ratio of our original concentration of benzoic acid, C6H5, COOH, and we divide that by our constant, Ka, and as long as this is over 100, then the value of X really is going to be so small compared to what I'm subtracting it from that it's really going to be negligible in our calculations. And you can see here, we have 0.027 divided by 6.5 times 10 to the minus 5. And we get about 415, which is clearly bigger than 100. So it's okay if we cross that out. Now, if that ratio was less than 100, you can't cross that out. You're going to have to do the ugly math there. Okay? Let me just free up some space here. And let's do the math. So we'll multiply both sides by 0.027. So I'm going to do that over here. So 6.5 times 10 to the minus 5 times by 0.027 is all equal to X squared. And then we're going to take the square root of both sides. When we do that and punch all that into our calculators, we get X equal to 1.9 times 10 to the minus 3 moles per liter. So what does that tell us? Well, we can go back to our equilibrium concentrations here. And subbing in for X, we can figure out the equilibrium concentrations of whatever we want. But what we're interested in, since I want to know pH, I want to know the equilibrium concentration of hydronium, which is just X. So this is actually the equilibrium concentrations for hydronium. So I can now calculate pH as minus the log of our hydronium concentration, right, which is 1.9 times 10 to the minus 3 moles per liter. And when we plug that into our calculator, we get a pH of 2.78. Now I also needed to figure out the concentration of hydroxide and the pOH. Remember our shortcut? pH plus pOH is equal to 14. Therefore, if we do 14 subtract 2.78, pOH is going to be equal to 11.12. Then we can find out the concentration of hydroxide by just using our equation 10 to the minus pOH. So when we substitute that in there, we get the concentration of hydroxide to be 7.6 times 10 to the minus 12 moles per liter. And that's the end of that question. All right, so this is the next question we're going to work on. It's number 13. It says the pH of hydrofluoric acid solution is 3. Determine the concentration of hydrofluoric acid in this solution. Okay, so let's write this out. So we have HF. Okay, and then we've got our water. This is going to be in equilibrium. Okay, so we're going to have 1H or 1 proton be donated to give us our hydronium. And then we're left with our fluorine ions. Now this one's actually already telling us the pH. So we can go right ahead and figure out what the concentration of hydronium is. Because the concentration of hydronium is going to be equal to 10 to the power of negative pH, where that negative pH is negative 3. So we plug that into our calculators and we get our concentrations to be 1.0 times 10 to the minus 3 moles per liter. So now we know the concentration of hydronium, but we want to know the concentration of the hydrofluoric acid. But now since we know one concentration, we can do an ice chart. So let's do our ice chart. I, C, E, where initially we don't know how much hydrofluoric acid is. So let's use that as our X. Okay, and we have start with nothing here. Now the change is going to be, we're going to gain 1.0 times 10 to the minus 3 moles per liter for both hydronium and fluoride. Whereas hydrofluoric acid is going to lose that amount since this is all a 1-to-1 ratio. So that's minus 1.0 times 10 to the minus 3. So our equilibrium concentrations, this one's going to be X minus 1.0 times 10 to the minus 3. And these are all just 1.0 times 10 to the minus. I'm writing this number out a lot. That's okay. So now that we have our ice chart, let's go ahead and set up our equation for our equilibrium law. So we have our acid constant is equal to the concentration of the product of our products. That's always hard to say. So hydronium and fluorine divided by the concentrations of our reactants. But water is a liquid, so that gets put into our constant. So we're just left with concentration of hydrofluoric acid. Now that's what we're looking for, okay? Which is going to be X. So Ka, that we can look up on one of our charts, or you can Google what the acid constant is for hydrofluoric acid. It is 3.5 times 10 to the minus 4. And so this is going to equal, we've got 1 times 10 to the 3 times 1 times 10 to the 3. So that's 1.0 times 10 to the negative 3 squared all over X minus 1.0 times 10 to the negative 3. Now, can I drop this 1.0 times 10 to the negative 3? If you look at our constant, that number is definitely not going to be greater than 100. So no, we can't drop it this time. We have to do the math. So let me make some room. All right, so let's go ahead and do this math. So we're going to multiply both sides by that wonderful bracket. So we have 3.5 times 10 to the minus 4, all times by X minus 1 times 10 to the minus 3 is equal to 1 times 10 to the minus 3 squared. Okay, so this term we're just going to have to distribute into both. So we have 3.5 times 10 to the minus 4 times x. And then we multiply those terms together, and we get 3.5 times 10 to the minus 7, which equals, if we square that term, we get 1 times 10 to the minus 6. Okay, let's bring this term to the other side and add them. So now we have 3.5 times 10 to the minus 4 times x is going to equal to 1.35 times 10 to the minus 6. Okay, now let's divide both sides. We're almost there. We're almost there. Times 10 to the minus 4. And we will have figured out what x is. Now hopefully we haven't lost sight of what x actually is and what we're solving for, but x turns out to be 3.9 times 10 to the minus 3 moles per liter. So definitely it was a good thing we never dropped this value, because that is too close to our Ka value. So the ratio was not more than 100. And if we haven't forgotten, x is, if you go back and look at our ice chart, we defined as the initial concentration of hydrofluoric acid. So we're done. All right, this next question is a great question, can definitely appear on a test. I don't know if my students heard that, but I hope you did. So here we have an ammonia cleaner, has a pH of 11.35. Determine the mass of ammonia in 0.5 liters of this solution. So first we have this ammonia solution. So let's write this out, this equilibrium. So we have ammonia, and then we have water, and that's going to be an equilibrium. So ammonia is going to take one of those hydrogens. So it's going to become ammonium. And then we're left with our hydroxide ion. All right, so this is a weak base. Now they give us the pH. So what we can do is we can start by finding the pOH. pOH is just going to be 14 minus that pH, 11.35. All right, so the pOH is therefore 2.65. And once we have pOH, we can find the concentration of hydroxide ions in the equilibrium, and that is going to be 10 to the minus pOH. So when we substitute that number in there, we get a concentration of 2.24 times 10 to the minus 3 moles per liter. All right, but what we want is we want the concentration of ammonia. Because if we had that, then we could work with the volume and work backwards and backwards to get the mass. Now we found the concentration of hydroxide. Right, now you can't do stoichiometry. This is equilibrium, so we have to use our equilibrium law. So Kb. Okay, so our base constant is equal to the concentration of the products of our products. I just love saying that. So NH4 plus and OH minus all over the concentration of NH3 ammonia. Okay, so let's do our little ice chart on the side there. So I, C, and E, where when we have ammonia as 1, ammonium, and hydroxide. So 1, 2, and 3. Initially, we have some ammonia. I don't know how much, so let's label X. Right? And then the change, well, we know the change because we know how much hydroxide we end up getting. So the equilibrium of our hydroxide is 2.24 times 10 to the minus 3. So to get that, we would have had to add that, 2.24 times 10 to the minus 3. Now looking at our ratios, which is 1, 1, 1, therefore we also added it here, 2.24, 10 to the minus 3, and we would have had to subtract it here, 10 to the minus 3. Okay, so our equilibrium concentrations are therefore as follows, where what we're interested in, ammonia, is X minus 2.24 times 10 to the minus 3. Let's put all of that into our equilibrium law. Now you can look up the base constant for ammonia, and it turns out to be 1.8 times 10 to the minus 5. And so that's going to equal, we have these two times each other, so 2.24 times 10 to the minus 3. We're going to square that, all divided by, for ammonia, we have X minus 2.24 times 10 to the minus 3. Now I'm banking this is going to be pretty small. Right? So let's just cancel it. And once we figure out what X is, we can double check just to make sure that we made a reasonable assumption there. But for now, let's cancel it and solve. Okay, so solving it would then be easy. You could just cross multiply. So X is equal to 2.24 times 10 to the minus 3 squared divided by 1.8 times 10 to the minus 5. So when we do that, we get X is equal to 0.279 moles per liter. Right? And so indeed, if I were to take that concentration and divide by our base constant, that is definitely a number that is much, much larger than 100. So that assumption we made previously, perfectly reasonable. Now that we know what the concentration of ammonia is, and we know that the volume is 0.5 liters, we can work backwards to figure out how many moles we have. Okay, so the number of moles, N, is going to equal our concentration times our volume. So we have 0.279 moles per liter times our volume, which is 0.5 liters, and we get 0.139 moles. See how close we are to the answer? So now we know how many moles of ammonia we have. We just need to know the mass. Okay, so we're going to say that the mass of ammonia is equal to the number of moles times our molar mass, which we can check. So our moles is 0.139, and our molar mass of ammonia is 17 grams per mole. So now it was a journey, but we got 2.4 grams. Great question. All right, here's the last question. Now, there's no calculations involved with this one, but we are going to look over strong and weak acids and bases. So predict whether the following solutions are acidic, neutral, or basic. So let's start with A. So with A, we have potassium iodide. Now, potassium iodide, okay, when placed in aqueous solution, is going to completely dissociate. Right? So we're going to have potassium ions, and we're going to have iodine ions. Okay, so the ions of strong acids and bases produce neutral solutions. So this one's going to be neutral. All right, let's look at the next one. So here we have NH4Cl. So NH4Cl, well, let's first, if we have that in water, let's first have it dissociate. So we're going to get ammonium ions, and we're going to get chlorine ions. However, ammonium ions will collide with the water molecules. And when that happens, one of the hydrogens is going to be donated to the water molecule. Now this is going to be in equilibrium, and we're going to get hydronium plus ammonia. So this is acidic. So this is slightly acidic. So let's do one more. I'm going to go and do C now. So we have sodium carbonate. Let's first dissociate that into our sodium atoms and carbonate. Now, carbonate, however, when it collides with water, we are going to have another equilibrium solution where in this case, it's going to steal a hydrogen from the water molecule. So we're going to get HCO3 plus OH negative. Basic solution. All right, now since we're having so much fun, let's do one more question, because this question is another great question that can appear on a test. Wonder if my students heard that. They'll let me know. Okay, so explain how sulfur trioxide, which is an atmospheric pollutant, contributes to acidic rain. So sulfur trioxide, so SO3, which is a gas, and we're going to have water, of course, in the atmosphere. Okay, but sulfur trioxide is a non-metal oxide, and non-metal oxides will produce acidic solutions. So if we look at this as an equilibrium, we're going to get H2SO4, which is sulfuric acid. Now, since I just showed this example of a non-metal oxide producing an acidic solution, let's just look at, say, if you had calcium oxide. Okay, so calcium oxide mixed with water, that'll give us an equilibrium. But in this case, right, we are going to get calcium ions and hydroxide ions. So whereas a non-metal oxide produces an acid, a metal oxide will produce a base. I hope that tutorial helped everyone. If you have any questions, you can always let me know in the comments.